Next example 6.6. So that the angular momentum about any point of a single particle moving with constant velocity remains constant throughout the motion. Now see here, suppose here we consider a particle which one is moving with constant velocity v in horizontal direction as shown in the figure, and the reference point here we have to calculate angular momentum about any point. So that any point here we consider that is point P. At a particular instant when particle is at position P, the position vector of that particular particle with respect to this reference point, that is R, as shown in the figure. And here the angle between position vector R and velocity v, that is theta. So on this side the angle that will be also theta. Now angular momentum of this particle with respect to this reference point, that we can write L equal to R cross P, where P that is its linear momentum, which is equal to m into v. Okay. So here the magnitude, that is magnitude L equal to R P sine theta, or we can write R M V sine theta. Now here draw a normal from this reference point to the velocity vector, or we can say line of action of the velocity vector, that is OM. So from figure you can say if this angle is theta, magnitude of OP, that is R, then OM that is equal to R sine theta. So in this particular equation we can write mv into R sine theta, but that R sine theta that is equal to OM. So here mv is what? mv that is the magnitude of linear momentum, and OM that is the perpendicular distance of linear momentum with respect to given reference point. But as per definition, here we can say this mass is constant, velocity given to you constant, so this m into v, magnitude of linear momentum, that is constant one, and from figure we can observe this thing, this perpendicular distance that also remains constant. Because see here, suppose at some instant your particle is somewhere here, right? So if your particle is somewhere here, then in that situation you can take position vector here R dash, and suppose the angle, this one is theta dash, so this will be also theta dash. So this OM that you can write, that is R dash sine theta dash. Okay, but after all this R dash sine theta dash, that is OM. So with respect to this position of the particle, if you write down the angular momentum, then also you will get the same thing, mv into R dash sine theta dash, but that is equal to OM, right? It implies that for any position of the particle here, we can say this thing, this perpendicular distance of linear momentum with respect to this reference point, that remains constant one. So we can say if mv is constant, R sine theta that is constant, then L that is constant. Now here the direction of angular momentum, that is constant one, as well as its magnitude, that is also constant. It implies that it does not change with time. So in other words, we can say L remains constant here with respect to any reference point. Clear to all of you?